Hello, and welcome to this tutorial on deep learning. My name is Douglas, and for the next hour or so, I will be discussing deep learning and TensorFlow, the TensorFlow environment, in order to show you an example of deep learning. There are several innovative and interesting applications of deep learning, one being identifying a geographical location based on a picture. Now, the way this works is by training an artificial neural network with millions of images, which have their geolocation tagged. And when we add a new picture, the network will be able to identify the geolocation of this new image. For example, you have all these images with perhaps significant monuments or significant locations, and you train with millions of such images. And then when you feed another image, though it may not be exactly the same as the one that was used for training, it would be able to identify and recognize, for example, that this is a picture from Paris because it recognizes the Eiffel Tower. Now, if we take a closer look at the way it works internally, by peeking under the hood, so to speak, these images are digital information in the form of pixels, and each image has a different size. They might be 256 by 256 pixels resolution, where each pixel has maybe a certain grade of color, and all that is fed into the neural network, which then gets trained based on this information and is able to recognize and extract the features, and thereby is able to identify these images and the location of these images. Then, when you feed a new image based on the training, it will be able to figure out where this image is from. So that's really the basics of how it works. So in this tutorial, we will cover what is deep learning and why do we need deep learning. One of the main components of deep learning is a neural network. So we will look at that. We will define a perceptron and how to implement logic gates using perceptrons and like and nor and so on using perceptrons. The different types of neural networks and applications of deep learning. We will see how neural networks work. For instance, how do we train neural networks? We'll end up with a small demo code, which we will take you through in TensorFlow. Now, in order to implement deep learning, there are multiple library or development environments that are available, and TensorFlow is one of those. So the focus at the end of this will be how to use TensorFlow to write a piece of code using Python as a programming language. Now, so we will use an example, which is a common one in the world of deep learning, which is handwriting number recognition, commonly known as MNIST database. So we'll look at MNIST database and how we can train a neural network to recognize handwritten numbers. So that's what we're going to cover in this video. So let's get started. Now, what is deep learning? Deep learning is a subset of a high-level concept known as artificial intelligence. Now, I assume that you've heard of or are already familiar with the term artificial intelligence. So artificial intelligence is like the high-level concept, if you will, and in order to implement artificial intelligence applications, we use what is known as machine learning. And then a subset of machine learning is deep learning. Now, machine learning is a more generic concept, and deep learning is one type of machine learning, if you will. We will see a little bit later and in future slides more detail of how deep learning is different from traditional machine learning. But to start with, we should mention that one of the differentiators between deep learning and traditional machine learning is that deep learning uses neural networks. We'll talk more about neural networks here and how we can implement neural networks, etc., as part of this tutorial. So if we look deeper into deep learning involves working with complicated unstructured data as compared to traditional machine learning, where we normally use structured data. Now in deep learning, the data would be primarily images or words or maybe text files, and include a large amount of data. Deep learning can handle complex operations. It involves complex operations, that is. Another difference between traditional machine learning and deep learning is that the feature extraction happens pretty much automatically. Now, in traditional machine learning, feature engineering is done manually. Therefore, data scientists have to do feature engineering and feature extraction. But in deep learning, that happens automatically. So, for large amounts of data, complicated unstructured data, deep learning gives very good performance. So, as I mentioned, one of the secret sources of deep learning is neural networks. So, what is a neural network? Neural networks are based on our biological neurons. The whole concept of deep learning and artificial intelligence is based on the human brain. And the human brain consists of billions of tiny interconnected neurons. You can see here how a biological neuron looks. And here's how an artificial neuron looks. So, neural network is basically a simulation of our human brain. The human brain has billions of biological neurons, and we are trying to simulate the human brain using artificial neurons. So, if we look closer at a biological neuron, it has dendrites. The corresponding component of an artificial network or an artificial neuron would be inputs. They receive the inputs through the dendrites. Then there is the cell nucleus, which is basically the processing unit in a way. In the artificial neuron, there is also a piece which is the equivalent of the cell nucleus. Then, based on the weights and biases, which we will discuss later, the input gets processed, which results in an output. In a biological neuron, the output is sent through a synapse. And in an artificial neuron, there is the equivalent of that in the form of an output. Biological neurons are also interconnected. There are billions of neurons that are interconnected in the same way artificial neurons are also interconnected. So the output from one neuron will be fed as an input to another neuron and so on. In a neural network, one of the basic units is a perceptron. What is a perceptron? A perceptron can be considered one of the fundamental units of a neural network. It can consist of one neuron, or it could be more than one, but you can create a perceptron with a single neuron. It could be used to perform certain functions. It can be used as a basic binary classifier, meaning it could be trained to do some basic binary classification. So this is what a basic perceptron looks like. This is nothing but a neuron. So you have your inputs x1, x2, and xn. Then there is the summation function. Then there is what is known as an activation function. And based on this input, what is known as a weighted sum, the activation function gives an output of either 0 or 1. So we say that the neuron is either activated or not. That's basically how it works. So you get the inputs, and each of these inputs are multiplied by a weight, and there is a bias that gets added, and the sum of these gets fed into the activation function, which results in an output. If the output is correct, it is accepted, and if the data is wrong, there's an error, and the error is fed back, and the neuron then adjusts the weights and biases to give a new output, and so on and so forth. And that's what's known as the training process of a neuron or a neural network. There's a concept called perceptron learning. Perceptron learning is one of the very basic learning processes. The way it works is somewhat like this. You have these inputs like x1 to xn, and each of these inputs is multiplied by a weight. This is the equation. So that sum, wi, xi, sigma of that, which is the sum of these, the product of x and w is added up, and then a bias is added to that. The bias is not dependent on the input or the input values, but the bias is common for one neuron. However, the bias value keeps changing during the training process. Then once the training is completed, the values of these weights, W1 and W2, and so on, and the value of the bias gets fixed. So that is basically the whole training process known as perceptron training. So the weights and biases keep changing until you get an accurate output. Then the summation is passed to the activation function. As you see here, this is WIXI summation plus B is passed to the activation function. Then the neuron gets either fired or not. And based on that, there will be an output. Then the output is compared with the actual or expected value, which is also known as labeled information. So this is the process of supervised learning, where the output is already known, and that is compared, and thereby we know if there is an error or not. If there is an error, the error is fed back, and the weights and biases are updated accordingly until the error is reduced to the minimum. So this iterative process is known as Perceptron Learning, or Perceptron Learning Rule. The error needs to be minimized. Until the error is minimized, the weights and biases keep changing through this iterative process. Again, the idea is to update the weights and the bias of the perceptron until the error is minimized. The error need not be zero. However, the idea is to reduce the error to minimum as possible. Again, this is an iterative process that continues until either the error is zero, which is unlikely, or the minimum possible given in these conditions. In 1943, two scientists, Warren McCullough and Walter Pitts, came up with an experiment where they were able to implement logical functions like and, or, and nor using neurons, which was a significant breakthrough in a sense. They were able to come up with the most common logical gates. They were able to implement some of the most common logical gates, which could take two inputs like A and B and then give a corresponding result. For example, in the case of an AND gate, A and B, the output is a B. In the case of an OR gate, it is A plus B, and so on and so forth. They were able to do this using a single layer perceptron. Now, for most of these gates, it was possible to use a single layer perceptron except in the case of NOR, and we'll see why that is in a little bit. So this is how an AND gate works. The input A and B, and the neuron should be fired only when both the outputs are 1. So if you have a 0, 0, the output should be 0. For 0, 1, it is again 0. For 1, 0, again it is 0. But for 1, 1, the output should be 1. So how do we implement this with a neuron? So it was found that by changing the values of weights, it is possible to achieve this logic. For example, if we have equal weights like 0.7 and 0.7, and if we take the sum of the weighted product, so for example, 0.7 into 0, and then 0.7 into 0 again, will give you 0, and so on and so forth. Now, in the last case, when both inputs are 1, to get an output that is greater than 1, which is the threshold, so only in this case, the neuron gets activated and there is an output. In all the other cases, there is no output because the threshold value is 1. So this is the implementation of an AND gate using a single perceptron or single neuron. As for an OR gate, the output will be 1 if either of these inputs is 1. As we can see here, in all the cases, the output is 1, except for here where we have to 0 is resulting in an output of 0. So how do we implement this using a perceptron? Well, once again, if you have a perceptron that with weights, for example, 1.2. Now, if you see here in the first case where both are 0, the output is 0. In the second case, when it is 0 and 1, 1.2 into 0 is 0, and then 1.2 into 1 is 1. And in this case, we see the output being 1.2. In the last case, where both inputs are 1, the output is 2.4. So during the training process, these weights will keep changing, and then at one point, where the weights are equal to W1 is equal to 1.2, and W2 is equal to 1.2, the system learns that it gives the correct output. So that is the implementation of an OR gate using a single layer perceptron or a single neuron. Now, XOR gate. This is one of the more challenging ones. They tried to implement an XOR gate with a single level perceptron, but it was not possible. And therefore, this was like a roadblock in the progress of neural networks. Subsequently, it was found that an XOR gate could be implemented using a multi-level perceptron, or MLP. In this case, there are two layers instead of a single layer, and this is how you can implement an XOR gate. You see here that X1 and X2 are the inputs. Then there is a hidden layer you see denoted here as H3 and H4. And then you take the output of that, and we get the output, noted as O5 here, and provide a threshold here. So then we see here the numerical calculation. So the weights in this case for X1, it is 20 and minus 20, and again 20 and minus 20. Then these inputs are fed into H3 and H4. So we see here for H3 the input is 0, 1, 1, 1, and for H4 it is 1, 0, 1, 1. Then if we look at the output, the final output where the threshold is 1, if you use a sigmoid with a threshold as 1, we see here in these two cases it is 0, and the last two cases it is 1. So this is the implementation of XOR. Now, in the case of XOR, when one of the inputs is 1, you will get an output, and that is what we are seeing here. In the case where both the inputs are 1 or both inputs are 0, then the output should be 0. That is known as an exclusive OR gate. Exclusive because only one of the inputs should be 1, and then you will get an output of 1, which is satisfied by this condition. So the XOR gate is a special implementation of a perceptron. Now that we have a good idea about what a perceptron is, let's take a look at a neural network. So we've discussed both the perceptron and the neuron. So let's turn our focus now to what a neural network is. Just like it sounds, a neural network is just a network of neurons. So there are 5 different types of neural networks. These are artificial neural network, convolution neural network, recursive neural network, or recurrent neural network, deep neural network, and deep belief network. So each of these types of neural networks have a special purpose. In other words, they can solve certain types of problems. For example, convolutional neural networks are very good at performing image processing and image recognition, and so on. Whereas recurring neural networks are very good for speech recognition and speech analysis, as well as text analysis. Now, each type has some special characteristics, and they are good at performing special types of tasks. With regard to some of the special applications of deep learning today is used extensively in the field of gaming. You've probably heard of AlphaGo, which is a game created by a startup called DeepMind, which was acquired by Google. And AlphaGo is an AI which defeated the human world champion Lee Siegel in this game of Go. So gaming is an area in which deep learning is being used extensively, and we see a lot of research happening in the area of gaming as well. In addition to that, nowadays there are neural networks known as generative adversarial networks, which can be used for synthesizing either images or music or text, etc. These can be used to compose music. That is, a neural network can be trained to compose a certain kind of music. Then autonomous cars. You might be familiar with Google's self-driving car. Today, a lot of automotive companies are investing in this area, and deep learning is a core component of these autonomous cars. So these cars are trained to recognize, for example, the road or the lane markings on the road, signals, any objects or obstructions that might be in front of the car. All of this involves deep learning, so that's another major application. Then robots. We've seen several robots, including Sophia. You may be familiar with Sophia, who was given a citizenship by Saudi Arabia. There are several such robots which are very human-like, and the underlying technology in many of these robots is deep learning. Medical diagnostics and healthcare is another major area where deep learning is being used. Within healthcare diagnostics, there are multiple areas where deep learning, image recognition, and image processing can be used. For example, for cancer detection. As you may be aware, if cancer is detected early on, it can be cured. One of the challenges, though, is the availability of specialists who can diagnose cancer using these diagnostic images and various scans and so on. So the idea is to train neural networks to perform some of these activities so that the load on the cancer specialists or oncologists is lightened. There's a lot of research happening here, and there are already quite a few applications that are said to be performing better than human beings in this area, whether it's lung cancer or breast cancer. So, healthcare is a major area where deep learning is being applied. Let's take a look at the inner workings of a neural network. So, how does an artificial neural network identify, or can we train a neural network to identify various shapes, such as squares or circles or triangles, etc., when these images are fed as the inputs? So, this is how it works. Any image is just digital information of the pixels. So, in this particular case, let's say this is an image of 28 by 28 pixels, and this is an image of a square. There's a certain way in which the pixels are lit up. So these pixels have a certain value. Let's say it may be from 0 to 256. And 0 indicates maybe it is black or dark, and 256 indicates it is white or completely lit up. So that would be an indication or a measure of how the pixels are lit up. So this is an image that consists of 784 pixels of information. So all this information contained inside the image can be, let's say, compressed into these 784 pixels. And the way that each of these 784 pixels is lit up provides information about what the image is. So we can train neural networks to use that information and identify the images. So let's take a closer look at how this works. So the value of each neuron, if it is close to 1, it is white, and if it is close to 0, it is black. So this is an animation of how this whole thing works. One of the ways of doing this is that we can flatten this image and take each of these 784 pixels and feed it into our neural network as an input. The neural network would consist of probably several layers. There could be a few hidden layers, and then there's an input layer and an output layer. So the input layer takes the value of these 784 pixels as an input, and then you get an output, which can be of 3 types, or 3 classes, which might be a square or a circle or a triangle. Now, during the training process, when you initially feed this image, it might say that it's a circle or a triangle. So, as a part of the training process, we then send that error back, and the weights and biases of these neurons are adjusted to correctly identify that this is a square. That is the training mechanism, really, that happens here. Now, let's take a look at a circle. This is the same way. So we feed these 784 pixels, and there's a certain pattern in which the 784 pixels are lit up, and the neural network is trained to identify that pattern. Again, during the training process, it will probably initially identify the image incorrectly, saying that maybe it's a square or a triangle. Then again, the error is fed back, and the weights and biases are adjusted until it gets the image correct. Now, once again, that is the training process. So now let's take a look at a triangle. So let's say if we feed another image consisting of a triangle. So this is a training process. We have trained the neural network to classify these images as triangles, circles, or squares. And now this neural network can identify these 3 types of objects. So if we feed another image, it will be able to identify whether it is a square or a triangle or a circle. So what's important to be observed is that when you feed a new image, it is not necessarily that the image, in this case, a triangle, is in the exact same position. The neural network actually identifies the patterns. So even if the triangle is, let's say, positioned here, not exactly in the middle, but maybe in the corner or on the side, it would still identify that the image is a triangle, which is the whole idea behind pattern recognition. So let's take a look at how this training process works. So we've seen that a neuron consists of inputs, it receives inputs, and then there's a weighted sum, which is nothing but this xi, wi summation of that plus the bias. And this is then fed to the activation function, and that in turn gives us the output. Now, during the training process, initially when you feed these images, let's say you send a square, it may identify it as a triangle, or maybe you feed it a triangle and it identifies it as a square, and so on. That error information is fed back, and initially these weights can be random. Maybe all of them have 0 values, and then it will slowly keep changing. As a part of the training process, the values of these weights, W1 and W2 up to Wn, keep changing in such a way that toward the end of the training process, it should be able to identify these images correctly. Until then, the weights are adjusted, and again, that is what's known as the training process. These weights have numeric values, could be 0.5, 0.25, 0.35, and so on. Could be positive or it could be negative. And the value that is input here is the pixel value. Now, they could be anything between 0 to 1. You could scale it from 0 to 1 or 0 to 256, whichever way you want. 0 being black and 256 being white, and all the other colors in between. So that is the input. So these are numerical values. This multiplication, or the product of wi, xi, is a numerical value, and the bias is also a numerical value. You need to keep in mind that the bias is fixed for a neuron, and it doesn't change with the inputs, whereas the weights are 1 per input. So that's one important point to note. But the bias also keeps changing. Initially, it will have a random value, but as a part of the training process, the weights, the values of the weights, W1, W2, Wn, and the value of B will change. Then ultimately, once the training process is complete, these values are fixed for this particular neuron. W1, W2 up to Wn plus the value of B is also fixed for this particular neuron. And so there would be multiple neurons, and there may be multiple levels of neurons here. And again, that's the way a training process works. So this is another example of a multi-layer where there are 2 hidden layers in between. And then you have the input layer, values coming from the input layer, and they can then go through hidden layers and finally to the output layer. And as you can see here, there are weights and biases for each of these neurons in each layer. And all of them change during the training process. At the end of the training process, each of these weights have a certain value, which becomes the trained model. And those values become fixed once the training is completed. Then there is something known as activation function. One of the components in neural networks is activation, and every neuron has an activation function. So there are different types of activation functions that are used. It could be a ReLU or a sigmoid and so on. The activation function is what decides whether a neuron should be fired or not. So whether the output should be 0 or 1 is decided by the activation function. The activation function in turn takes the input, which is the weighted sum. You'll recall we talked about wi, xi plus b. That weighted sum is fed as an input to the activation function, and then the output will be either a 0 or a 1. There are different types of activation functions, which were covered in an earlier video, which you might want to watch. So as a part of the training process, we feed the inputs, the labeled data or the training data, and then we get an output, which is the predicted output by the networks, in which we indicate as y hat. And then there's labeled data. Because for supervised learning, we already know what the output should be. So that is the actual output. During the initial process before the training is complete, obviously there will be errors, and that is what is known as a cost function. So the difference between the predicted output and the actual output is the error. Now, the cost function can be defined in different ways. There are different types of cost function. In this case, it is the average of the squares of the error. So all the errors are added, which can sometimes be called the sum of the squares, sum of square errors, or SSE. That is then fed as feedback in what is known as backward propagation or backpropagation. And that helps the network adjust the weights and biases. So the weights and biases get updated until this value, the error value or the cost function, is minimal. There is an optimization technique which is used here called gradient descent optimization. So this algorithm works in a way that the error, which is the cost function, needs to be minimized. There's a lot of mathematics involved in this. For example, they find the local minimum, the global minimum using differentiation, and so on. But the idea is this: the goal of the training process is to reduce the error. So if we look at this as the cost function, in the beginning or at certain levels, the value of the output or of the cost function is very high. So the weights have to be adjusted in such a way, the weights and the bias, so that the cost function is minimized. So this optimization technique called gradient descent is used. This is known as the learning rate. So for gradient descent, you need to specify what the learning rate should be. So you want the learning rate to be optimal, because if you have a very high learning rate, the optimization will not converge, because at some point it will cross over to this side. On the other hand, if you have a very slow learning rate, it might take forever for that to converge. So we want to come up with the optimum value of the learning rate. Once that is done, using gradient descent optimization, the error function is reduced, and you come to the end of the training process. So this is another way of looking at gradient descent. Over here, we see the cost function, the output of the cost function, the output of the cost function, which has to be minimized using the gradient descent algorithm. And these are the parameters, so weight could be one of them. Initially, we start with random values and costs will be high, and as the weights keep changing in such a way that the cost function comes down. At some point, it may reach a minimum value and then start to increase. So that is where the gradient descent algorithm decides it has reached the minimum value, and it will try to stay there. This is known as the global minimum. So these curves were drawn for explanation purposes. However, these changes could be erratic. Sometimes there may be a local minimum here, and then a peak, and then so on and so forth. But the whole idea of gradient descent optimization is to identify the global minimum and find the weights and the bias at that particular point. So that's sort of an overview of gradient descent. Now here's another example where we see these multiple local minimums. You see here at this point it is coming down, and this looks like it might be the minimum value, but it's not. And we see the global minimum here. So the gradient descent algorithm will make an effort to reach this level and not get stuck here at a local minimum. So the algorithm knows how to identify the global minimum, and it does that during the training process. Now, in order to implement deep learning, there are multiple platforms and languages that are available, but the most common platform nowadays is TensorFlow. We created this video to give you an overview of TensorFlow. So we're going to do a quick demo on how to write a TensorFlow code using Python. TensorFlow is an open source platform created by Google. So let's take a quick look at the details of TensorFlow. So this is a library, a Python library. So you can use Python or another language, or other languages are also supported, like Java, among others. But Python is the most common language that is used. So this is basically a library that is used for developing deep learning applications, especially using neural networks. It consists of primarily two parts. One is the tensors, and the other is the graphs or the flow. That's why it's called TensorFlow. Now, tensors are like multi-dimensional arrays. That's sort of one way of looking at it. And usually you have a one-dimensional array. First of all, you can have what is known as a scalar, which means a number. And then you have a one-dimensional array, something like this, set of numbers so that it's a one-dimensional array. Then you can have a two-dimensional array, which is like a matrix. Beyond that, sometimes it gets difficult. So this is a three-dimensional array, but TensorFlow can handle many more dimensions. So it can have multi-dimensional arrays. And that's really the strength of TensorFlow, which makes deep learning computation much faster, which really is the reason TensorFlow is used for developing deep learning applications. So TensorFlow is a deep learning tool, and this is the way it works. So the data basically flows in the form of tensors. The way the programming works is that first you create a graph of how to execute it. And then you execute that graph in what is known as a session. And we will see this in the TensorFlow code as we move forward. So all the data is manipulated or managed in tensors, and then the processing happens by using these graphs. So tensors have ranks, and the ranks of a tensor is sort of like the dimensionality. For example, if it is scalar, in other words, just one number, the rank is supposed to be 0. It could be a one-dimensional vector, in which case the rank is supposed to be 1. And then you can have a two-dimensional vector, like a matrix. In that case, we say the rank is 2. Then if it's a three-dimensional array, the rank is 3, and so on. It could have more than 3 as well, so you could have multidimensional arrays in the form of tensors. So what are some of the properties of TensorFlow? I think today it is one of the most popular deep learning platforms or libraries. It is open source, developed and maintained by Google. One of the most important things about TensorFlow is that it can run on either CPUs as well as GPUs. GPU is a graphical processing unit, and CPU, of course, is a central processing unit. Previously, GPU was used primarily for graphics, which is the reasoning for the name. Now, GPU cannot perform generic activities very effectively like CPU can, but it can perform iterative actions or computations extremely fast, much faster than CPU. Which makes it very good for computational activities. And in deep learning, there's a lot of iterative computation that happens, so in the form of matrix multiplication and so on. So GPUs are very well suited for this kind of computation. And again, TensorFlow supports GPU as well as CPU. So there's a certain method for writing code in TensorFlow, as we will see when we get into the code. Of course, TensorFlow can be used for traditional machine learning as well, but that would be overkill. So in order to gain an understanding, it might be good to start writing code for a normal machine learning use case so that you can get the hang of how TensorFlow code works, and then you can move into neural networks. So that's just a suggestion. But if you're already familiar with how TensorFlow works, you could probably go straight into the neural networks part. In this tutorial, we will take the use case of recognizing handwritten digits. So this will be a good example of deep learning. Now, the MNIST database is a nice database that has images of handwritten digits nicely formatted. Because very often in deep learning and neural networks, we end up spending a lot of time preparing the data for training. However, with MNIST database, we can avoid that because the data is in the right format, which can be used for training. MNIST also offers a bunch of built-in utility functions that we can use right away without worrying about writing our own functions, which is really one of the reasons why MNIST database is very popular for training purposes. Now, initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. It has a collection of 70,000 handwritten digits, a large part of which are for training. Then you have a test, just like in any machine learning process, and then you have validation. So all of them are labeled. So you have the images, and they are labeled. And these images look somewhat like this. We see handwritten images collected from many individuals. Now, these samples are handwritten by human beings, and these numbers go from 0 to 9. So different people have written these numbers, and the images have been copied and are formatted in such a way that it is very easy to handle. So that's a little about the MNIST database. Now, where we're going to implement this in our TensorFlow is we will feed this data, the training data, along with the labeled information. Basically, these images are stored in the form of pixel information, as we saw in a previous slide. But each of these images is nothing but pixels. So an image is nothing but an arrangement of pixels. And the value of the pixel is either lit up or it is not, or it may be somewhere in between. That's really how the images are stored and how they're fed into the neural network for training. Now, once the network is trained, when you provide a new image, it will be able to identify that image within a certain percentage of error, of course. So for this, we'll use one of the simpler neural network configurations called Softmax. For simplicity, what we will do is flatten these pixels instead of looking at them in a two-dimensional arrangement. And so we'll just flatten them all. For example, it starts from here. It's a 28 by 28 pixel. So there are 784 pixels. So pixel number 1 starts here and goes all the way up to 28, and then 29 starts here and goes up to 56, and so on. And pixel number 784 is here. So we take all these pixels, flatten them out, and feed them like one single line into our neural network. So this is what's known as a Softmax Layer, which what it does is once it's trained, it will be able to identify what digit this is. So in this output layer, there are 10 neurons. Each signify a digit, and at any given point, when you feed an image, only one of these 10 neurons gets activated. For example, if this is trained properly, and if you feed a number 9 like this, then this particular neuron gets activated. So you get an output from this neuron. So let me just use a pen or a laser to show you here. So you're feeding number 9, and let's say this has been trained. So if you're feeding a number 9, this will get activated. Now, let's say you feed 1 to the trained network. Then this neuron will get activated. If you feed it 2, then this neuron will get activated, and so on. You get the idea. So this is one type of a neural network, or an activation function known as Softmax Layer, which is what we'll be using here. So this is one of the simpler types for quick and easy understanding. So this is how the code would look. We'll go into our lab environment in the cloud. We'll go there and show you in just a minute. But quickly, this is how the code will look. So I'll just go over this briefly here, and then we'll go into the Jupyter Notebook where the actual code is, and we will run that as well. So first of all, we're using Python here. And you can see this syntax here is Python language. Now, the first step is to import the TensorFlow library. Now, we do this by using a line of code. Import TensorFlow as TF. TF is just for convenience, and you could name it anything you want. Once you do this, the TensorFlow is available as an object identified as TF, and then you can run its methods and access its attributes and so on. Now, MNIST database is actually an integral part of TensorFlow, which is the reason we always use this example, MNIST database, as an example. So we simply import MNIST database as well as using this line of code. And then you slightly modify this so that the labels are in this format, what is known as one hot true, which means that the label information is displayed like an array. So let me just use a pen to show you what this is. So when you use this one hot true, what happens is each label is stored in the form of an array of 10 digits. And let's say the number is 8. So in this case, all the remaining values, there will be a bunch of zeros. So this is like the array at position 0. This is at position 1, position 2, and so on and so forth. Let's say this is position 7. Then this is position 8. That will be 1 because our input is 8. And again, position 9 will be 0. So what this means is 1 hot equals true, will kind of load the data in such a way that only one of the digits has a value of 1. So based on which digit is 1, we know what the label is. And so in this case, the 8th position is 1. So we know that the sample data, the value is 8. Similarly, if you have a 2 here, let's say, then the label information will look something like this. So you have your labels. And then first you have a 0 in the 0 position and a 0 in the first position. And the second position will be a 1, which indicates number 2. Then your third position is 0 and so on. So that is the significance of one hot true. So then we can take a look at the data by displaying the data. And as I said earlier, you can see that this is displayed in the form of numbers, and each one of these is pixel values, so you won't see the images in this format. But there is a way to visualize the image, and we'll take a look at that in a bit. So this tells you how many images there are in each set of the training. And we see there are 55,000 images in the training, and the test set has 10,000. And validation, there are 5,000. So altogether, there are 70,000 images. Okay, let's just move on then. Okay, so you can view the actual image using the matplotlib library. And we see here the code used for viewing the images. You can view them in color or you can view them in grayscale. And the CMap here defines which way we will view that. Then we have the maximum and minimum values of the pixel values, where you see the maximum here is 1, because this is a scaled value. 1 means it is white, and 0 then means it is black. And it could be anywhere between black and white. So in order to train the model, there's a certain way to write the TensorFlow code. The first step is to create some placeholders, and then you create a model. In this case, we'll use the Softmax model, and one of the simplest models. Placeholders are primarily to get the data from outside into the neural network. So this is a very common mechanism that is used. Then, of course, you will have variables. You may remember these are your weights and biases. So when there are, in our case, there are 10 neurons, and each neuron has 784, because each neuron takes all the inputs. So if we go back to our slide here, actually each neuron takes all 784 inputs. So here's the first neuron, which takes all 784 inputs. The second neuron takes all 784 inputs, and so on. So each of these inputs needs to be multiplied by a weight, and that's what we're referring to here. So this is a matrix of 784 values for each of the neurons. In other words, 10 by 784 matrix, because there are 10 neurons. And then there are biases. Now, you may remember that the bias is there's only one per neuron. So it's not one per input, unlike the weights. So therefore, there are only 10 biases because there are only 10 neurons in this case. So we're creating a variable for the biases. So this is something a little new in TensorFlow. Unlike our regular programming languages, where everything is a variable, here the variables can be of 3 different types. You can have placeholders, which are primarily used for feeding data. You have the variables, which can change during the course of computation. And then the third type, which is not shown here, are constants, which would be fixed numbers. In regular programming language, you would have all variables, or perhaps variables and constants, but in TensorFlow, you have all 3, placeholders, variables, and constants. And then you create what is known as a graph. So TensorFlow programming consists of graphs and tensors, as we discussed earlier. So this would be considered a tensor. And then the graph tells how to execute the implementation so that the execution is relied in the form of a graph. In this case, what we're doing is a multiplication. TF, you remember the TF was created as a TensorFlow object. So let's just go back here. So TF is available here. Now TensorFlow has what is known as a matrix multiplication, or matmul function. And that is what is being used here in this case. So we are using the matrix multiplication of TensorFlow. So you'll multiply your input values, x with w. So in summary, xw plus b, you're just adding b. Similar to one of the earlier slides we saw where sigma xi wi. That's what we're doing here. Matrix multiplication is multiplying all the input values with the corresponding weights and then adding the bias. So that is a graph we created. And then the next we need to define our loss function and our optimizer. So in this case, we are going to use the TensorFlow APIs. So TF.NN, Softmax, cross entropy with logits is the API that we will use. And reduce mean is the mechanism which says that you reduce the error. Then the optimizer for doing the correction of errors, we are using the gradient descent optimizer, which we talked about earlier. So for that, you need to specify the learning rate. You remember we saw a slide somewhat like this, where you defined what the learning rate should be and how fast you need it to come down. That's the learning rate. And again, this needs to be tested and tried in order to find out the optimum level of the learning rate. It shouldn't be very high, in which case it would not converge. And again, it shouldn't be too low because it will take too long. So you define the optimizer and then you minimize for the optimizer. And that will kickstart the training process. So far we've been creating the graph, and in order to actually execute the graph, we create what is known as a session, and then we run that session. And once the training is completed, we specify how many iterations we want it to run. For example, in this case, we are saying 1,000 steps, which becomes the exit strategy in a way. So you specify the exit condition. So the training will run for 1,000 iterations. And once that's done, you can evaluate the model using some of the techniques shown here. So let's just take a look at the code quickly and see how it works. So this is our cloud environment. Now, you can install TensorFlow on your local machine as well. I'm showing you this demo on our existing cloud, but you can also install TensorFlow on your local machine. We have a separate video on how to set up your TensorFlow environment, which you can watch that if you want to install TensorFlow on your local environment. Or you can use any other cloud service, for example, Google Cloud, Amazon, or Cloud Labs. Any of these could be used to check out the code. Okay, so this is started. And we will log in. All right, so this is our deep learning tutorial code. And this is our TensorFlow environment. So let's get started. So we've already seen a little bit of code here in the previous slides. And now we'll see the code in action. So the first thing we need to do is import TensorFlow, and then we will import the data. And then we need to adjust the data in such a way that one hot encoding is set to true, as I explained earlier. In this case, the label values will be shown appropriately, and we can just check and see what type of data we are using. So these here are the data sets, Python data sets. And if we check the number of images, we can see how this looks. Like this is an array of type float32. Also, if we want to see the number of training images, we see there are 55,000, and then we see 10,000 test images, and then 5,000 validation images. Now let's take a quick look at the data itself, visualization. So we'll use matplotlib for this. And if we take a look at the shape, now the shape gives us the dimension of the tensors, or the arrays, if you will. So in this case, the training data set, you can see the size of the training data set using the method shape. It says there are 55,000 by 784. And again, remember the 784 is the 28 by 28 pixels. So that's what it is showing. So let's take one image, and we'll take the first image and look at the shape. So we see the size is only 784. We could also look at the data of the first image itself, and this is what we see. So now most of it will be zeros, because you can imagine in the image only certain areas are written on, so that's why the rest is blank, which is why we'll have mostly zeros. Again, it's black or white. Then the rest of the values are scaled, so they are between 0 and 1. And this is what we see here. So we have these different locations with values and other locations with zeros. So that's how the data is loaded. And then if we want to see what the value of the handwritten image, or if you want to view it, this is how you view it. So you build this reshape. So matplotlib has this feature to show you these images. So we will actually use the IMShow function. And if you use the parameters appropriately, you will be able to see the different images. Now I can change the values in this position for which image we are looking at. So let's say I want to look at and see what the image is, image 5,000. We see 5,000 is a number 3. Or if we say 5, what is a 5? It is an 8, or maybe 50. Another 8. So if you're wondering how I'm executing this code, Shift-Enter. If you're not familiar with Jupyter Notebooks, Shift-Enter is how you execute each individual cell. And then if you want to execute the entire program, you can come up here and say Run All. So that is how this code gets executed. Here again, we can see what is the maximum and minimum value of the pixel values, as I mentioned. These are scaled, and the values are between 1 and 0. Now, this is where we create our model. The first thing is to create the required placeholders and variables, which is what we're doing here. So we create one placeholder, and we create 2 variables, which are for the weights and the biases. So these 2 variables are actually matrices. And each variable has 784 by 10 actual values. So again, the 10 is for the number of neurons, and the 784 is the pixel values, which is 28 by 28 pixels. Then with the biases, as I mentioned, 1 for each neuron. So there will be 10 biases. They are stored in the variable noted B. Then we have the graph, which is basically the multiplication, the matrix multiplication, X and W and N. Then the bias is added for each of the neurons. And the whole idea is to minimize the error. So let me just execute this code. I think it's already executed. So then we define the Y value, which is basically the label value. So this is another placeholder. And we have X as one placeholder and Y true as a second placeholder. which will have values in the form of 10-digit arrays. And since we said one hot encoded it, the position that has one value indicates the label for that particular number. Then we have cross entropy, which is nothing but the loss function. Then we have the optimizer. We have chosen gradient descent as the optimizer. Then the training process itself. So the training process, which is done to minimize the cross entropy, which again is the loss function. So we define all of this in the form of a graph. Now, up to now, remember, we've not executed any TensorFlow code until now. We're just preparing the graph or the execution plan. That's how the TensorFlow code works. So the whole structure and format of this code will be completely different from how we normally do programming. So people with programming experience might find this a little difficult to understand. And it needs quite a bit of practice, and you may want to view this video a couple of times to better understand the flow, because TensorFlow programming is slightly different from normal programming. So some of you who have done maybe Spark programming, to some extent will be able to easily understand this. Although in Spark, the code itself is pretty straightforward behind the scenes. The execution happens differently. But in TensorFlow, the code is written in a completely different way. And the code doesn't get executed in the same way that it is written, which is something that you can learn through practice. Now, so far, what we've done up to here is to create the variables and set up the variables in the graph, and that's pretty much all. Basically defining what kind of network you want to use. For example, you may want to use Softmax and so on. So you have created the variables, the data, viewed the data, we've prepared everything, but have not yet executed anything in TensorFlow. So now the next step is the execution in TensorFlow. So the first step for doing any execution in TensorFlow is to initialize the variables. So anytime you have variables defined in your code, you need to run this piece of code always. So you need to create what is basically known as a node for initializing. So this is a node. You're still not executing anything here. You just created a node for the initialization. So let's go ahead and create that. And from here forward is where you will actually execute your code in TensorFlow. And in order to execute the code, what you will need is a session, TensorFlow session. So tf.session will give you a session. So there are a couple of different ways you can do this, but one of the most common methods of doing this is what is known as a with loop. So you have with tf.session as ses with a colon here. This is like a block, the starting of a block, and these indentations tell how far the block goes. And this session is valid until the block gets executed. So that is the purpose of creating this with block. So with tf.session as ses, and then ses.run init. Now ses.run will execute a node that is specified here. So for example, we are saying here ses.run. Ses is basically an instance of the session. So here we are saying tf.session. So an instance of the session gets created, and then we're calling that ses, and then we run a node within that, one of the nodes in the graph. So one of the nodes here is init. So we say run that particular node, and that is when the initialization of the variables happens. So now what this does is if you have any variables in your code, in our case we do, W is a variable and B is a variable. So any variables that we have created, you have to run the initialization of these variables, or you'll get an error. So that is what this is doing. So then within this block, we specify a for loop. So we say we want the system to run 1,000 iterations and perform the training. So that's what the for loop does. Run the training for 1,000 iterations. And what it is doing is basically it's fetching the data or these images. Remember, there are about 50,000 images, but it cannot get all the images in one shot because it would take a lot of memory and you'll have performance issues. So this is a very common way of performing deep learning training. You always do it in batches. So you may have 50,000 images, but you might do it in batches of 100 or maybe 500, depending on the size of your system and so on. So in this case, we are saying get me 100 images at a time and only training images. Remember, we only use the training data for training purposes, and we use the test data for test purposes. So you might be familiar with machine learning, but in case you aren't in machine learning, this is not specific to deep learning. Machine learning as well, you have what is known as a training data set and a test data set. Your available data, you will be typically splitting into two different parts and using the training data set for training purposes. And then to see how well the model has been trained, you use the test data set to check the accuracy of the model. So that's what we're doing here. Now, you can see here we are actually calling an MNIST function, mnisttrain.nextBatch. So this is the advantage of using an MNIST database because they have provided some very nice helper functions. Otherwise, we would have had to write the piece of code to fetch this data in batches, and that itself would be a lengthy exercise. So we can avoid all of that if we're using the MNIST database, and that's why we use this for the initial learning phase. So when we say fetch, what it will do is fetch the images into X and the labels into Y, and then you use this batch of 100 images, and you run the training session. So ses.run. And what we're doing here is running the training mechanism where it passes the images through the neural network and then determines the output. And then if the output is initially wrong, the feedback is given back to the neural network, and thereby all the W's and B's get updated until it runs 1,000 iterations. In this case, the exit criteria is that 1,000, but you could also specify, say, the accuracy rate or something like that as the exit criteria. So here it just says that this particular image was wrongly predicted. So you need to update the weights and biases. That's the feedback given to each neuron, and that is run through 1,000 iterations. And typically after 1,000 iterations, the model would have learned to recognize these handwritten images. However, it might not be 100% accurate. So once that is done, once the 1,000 iterations have run, you test the accuracy of this model by using the test data set. So this is what we are trying to do here. And the code may be a little complicated, especially if you're seeing this for the first time, but you need to understand the basic TensorFlow method. But basically, it's just comparing the output with what is actually there. So you have your test data, and you're trying to find out what is the actual value and the predicted value and seeing whether they're equal or not, tm.equal, and how many of them are correct and so on and so forth. Based on that, the accuracy is calculated as well. So this is the accuracy, and we are trying to determine how accurate the model is in predicting these numbers or these digits. So let's run this. This entire thing is in one cell, so we'll have to just run it in one shot. And this might take a little while. Let's see. Not bad. So it has finished 1,000 iterations, and what we see here as an output is the accuracy. So we see that the accuracy of this model is around 91%, which is pretty good. for such a short exercise within such a short time frame. However, in real life, this is probably not sufficient. So there are other ways to increase the accuracy, which we will see in some other tutorials. How to improve the accuracy, how to change maybe the hyperparameters like number of neurons or number of layers and so on, so that we can increase the accuracy beyond 91%. So what is a TensorFlow Object Detection API? It's an open source framework which is provided by the TensorFlow team. And there are trained models available, and the sample code, which is also available, which we can use in order to easily detect objects and images and videos. This is pretty robust and can detect objects fairly quickly. It's very easy for people to use. Even people with very little or no knowledge of machine learning or deep learning can also, with a little bit of Python programming knowledge, can actually use this API, this library, to build object detection applications. So this is a list of libraries that are required, and these have been shown in the code as well. The exact purpose of each of these libraries, or why it is required, is outside of the scope of this tutorial. But we can see in the code as we walk through how and why they are used. So the COCO dataset, COCO stands for Common Objects in Context. So this dataset consists of 300,000 images of 90 most commonly found objects, like chairs and tables, etc. This model has been trained, or in fact, a set of models have been trained on this data set. And this is pretty good to detect the most common objects and images and videos. So with that, let's get into the code. The first step is to import all these libraries, as we have shown you previously. A large part of this will be for doing some helper functions, or maybe visualizing the images and so on. So that's the reason they're required. So the exact details of each and every library is probably out of the scope of what we're doing here right now. But as a first step, we need to include these libraries and run the code. And then at a later time, we could maybe discuss what each library does. This will work with TensorFlow versions higher than 1.4. So you may have to upgrade if you're running a version lower than 1.4. So let me go ahead and execute this cell. We also need this line of code to make sure that once we run this object detection, the labeled images are displayed within the notebook. So some of you are familiar with this, and we will be importing some of these utility libraries, which we will be using for visualization purposes. So once the objects are detected, we need to display the information, what the object is and what percentage of confidence the model has, which is the reason for the utility functions. The next step is to prepare the model. As I said, we will be using an existing trained model. The TensorFlow team has actually provided these models. The one that we will be using is SSD with MobileNet. But you can use any one that is listed in this URL. So let me just show you this URL. These are a bunch of models, trained models that are readily available for anyone to use. These are open source models. If I scroll down, you can see some of them, the accuracy is higher, but they take longer. And others with lower accuracy that are much faster. So you can play around with some of these. But again, in this particular exercise, we are going to be using this SSD model, which is SSD MobileNet version 1. So in this cell, we are primarily creating a bunch of variables. For example, the name of the model, the path, and so on and so forth. Then we will be using these names in the next step, which is to download this model and install it locally. These are also referred to as frozen models. So once they are trained, you can extract or freeze the model, hence the name frozen model. So that others can use this without any further training. So this is where we download and extract our model locally. So this is going to take a little while, so I may have to pause the video and come back once it's done. This might take a bit, so let's see if it completes. I have a pretty high speed network, but even then, this will take some time. So let's take a look at this. That's done, and now this is done. So once that is done, we need to load some label mapping. And basically what this will do is your model, as you may be aware of by now, if you do some classification, the model will not give you an output as text. Rather, it will give numbers. So there are 5 classes, and it will say this belongs to class 1 or class 2 or 3 or 5 and so on. So the numbers will obviously not make any sense to the outside world. So we need to do some small mapping. So in this case, 1 may be a chair, 2 may be a table, 3 may be a pillow, and so on. So that kind of number to text mapping needs to be done, and that is what is being done in this particular cell. And then we have a helper code which will load the image and convert it into a NumPy array, which is what gets processed and used by the model to do the detection. So that is what this is. And a little bit later, you will be calling this function. Next is the preparation for detection. So here we are basically saying where the images are stored and how many images or what the naming convention or format of the images is. Now, if you want, you can modify this code. For example, currently I have test_images as my folder. So let me just show this to you. So this is my object detection folder, and I have a subfolder which is storing my images, which is test_images. So you can rename that folder and you could use that name in your code. Now, also, the format of these files, here we see a very simple format, which is the names of the files are like Beach 1, Beach 2, Beach 3, and so on. So I'm using beach as the team. Therefore, I have images that are related to beaches. So this is Beach 1, Beach 2, and Beach 3. And there are some others, but we'll use these 3 for our demo. So that's what we're calling out here. And the name of the image will be beach, something like j.jpg, which is the JPEG format. And within these braces will be 1, 2, or 3, depending on which image we are using. So the next step is to run inference on these images in a loop. And what we are basically doing here is getting these images one by one and then running through the model to find out what objects can be detected. And then against each of these objects, a box will be drawn, and that will be labeled with the name and percentage of accuracy or confidence that the model detects these objects. So that is the function here. And let me just run that piece of code. And here's basically where we are calling this function. So we are loading these images, and then we are calling this function for each image. And we are displaying this using matplotlib library. So let me just run this. It will take one image at a time and then detect the images. Now the beauty is that the same format for this code can be used for doing object detection in a video. And we have another video for doing object detection in a video. So most of the code out there will be reused from here, except that instead of reading the images from the local storage, we read the frames from the video. So there's a neat video reader that will be available, which will be shown in another video. Then frame by frame, we read the video and then pass that on to this function, and it will act as each of these frames is an image, and that will do the object detection for the entire video. So that's in a separate video, so maybe be on the lookout for that. And the information for that will be provided in the cards in the eye symbol. So that's a separate tutorial for object detection in video. So now that we have all the pieces together, the last cell is where all the action takes place. So let's run this and see how it looks. So this may take a little while. So now there are 3 images. So let's see what it detects. So there we go. So the first one, it has detected a person with 97% accuracy, which is pretty good. Okay, and the next image, it detects an umbrella and chair. There are a few other objects in that it was not able to detect, but we see the umbrella and it shows 63% accuracy or confidence, and the chair with 58%. Again, not bad. Now let's take a look at the next image. So here, these are balloons, hot air balloons, but the model thinks it's a kite, which is probably not that bad. It sees that there's something in the sky and therefore it thinks that it's a kite. And we see it detects that with 65% confidence. Okay, so that was pretty much all I wanted to show you in this particular tutorial about object detection in images. And with that, we come to the end of this tutorial. I hope you liked it and found the content useful. If you have any questions or comments, please feel free to place those below. And make sure to watch the other tutorial on object detection in videos. Thanks, and have a great day.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.